most of the time is if you have a hole in the graph, they're going to call that a removable discontinuity. I can't think of any problems where they actually just call it hole in the graph, that sort of informal language. But a hole in the graph just simply looks, you know, something like this, where you have this single point where the graph still connects, but that one value is not defined. Okay, it is called a removable discontinuity because if we put one single point right there, it would remove the discontinuity and our line would be continuous. So it would only take one single point. Now, for these discontinuities, it could look like a hole like this, or you could have like a point defined up here. That's also a possibility. So that point may be there, it may not. Both of those would still be considered a hole in the graph. Okay. Non-removable discontinuities are going to be found as either jumps in the graph, so it might be something like this, where you are traveling along and you jump from one graph to another, teleportation here, or they can be vertical asymptotes, which could look, you know, they could both go in one direction, like this. You could have one go up, one go down. You might have it just from one side. Those would be non-removable because you cannot fix those with just a single point. Okay, so we talked about these some in pre-calculus about how to tell if something is going to have these, but we're going to look at a few more types of equations than we looked at in pre-cal. So, discontinuities can be caused by negatives underneath the square root, zeros in the denominator of a fraction, a number less than or equal to 0 inside of a logarithmic function. Okay, that one's one we haven't looked at a whole lot, but you can't take a log of 0 or a negative number. A piecewise function that has a hole or a jump, and then some trig functions are also going to have asymptotes sort of built in, like our tangent graph looks, you know, it's got the squiggles that go up and there's those asymptotes there. So those are a variety of ways that you might see discontinuities for this. So we're going to find any x values for which f of x is discontinuous, and we're going to tell whether the discontinuity is removable or non-removable. These two types of problems are the ones we saw most often in pre-calculus when we're looking at rational functions. So with a fraction, what's going to give us a discontinuity is having a 0 in that denominator. So what you want to do for these problems is you want to factor top and bottom. So for this one, that numerator will not factor. The denominator, you don't have to factor out the 2, but it just makes it a little bit easier to factor if you do. And then so if we factor completely here, 2, we'd have an x and an x. We got to get -6 and a positive 1 in the middle, so we could do +3, -2. Now, when you're looking for discontinuities, you're looking at the bottom. Okay? So we want to look for discontinuities before we even worry about whether something will cancel. So we would have discontinuities not that I know of. I mean, you can make one. I would highly suggest on the AP exam, if you need to talk about discontinuity, just write it out. because it doesn't take that much longer, and if they don't recognize that abbreviation, it could cost you a point. And when you're talking about, like, you know, the higher stakes there, just write it out for that. Same thing with things like does not exist. Just write it out. You know, they're probably going to take does not exist, but what if they don't? You have just lost a point that you otherwise knew how to do. Because there are going to be some points we don't know how to do probably. We want to get every point that we can. So on your homework, I don't care that much. Know yourself, though. Like, are you setting up bad habits that you're going to also do on the test? There. So discontinuity, x is going to equal -3, and x will equal +2. You have discontinuities at those points, for sure. What we need to know is what type of discontinuity. So, the x plus 3 is going to cancel. What type of discontinuity do you have if that factor that goes with that 0 cancels? A whole. So, this is a whole, or what's the other word for it? Removable. Okay, I don't care, you can use either phrase, but you need to recognize removable because they're probably going to use that if it's written out in the problem. And then what are we going to have over here at x equals 2? That is going to be a vertical asymptote. And I'm being lazy there and abbreviating as well, but on the exam, I'd write it out, vertical asymptote. And that is non-removable. Everybody good there? All right, let's look at the second one. We need to factor that. We would have x plus 2, x plus 3 on the top, and x plus 1, x plus 3 on the bottom. So, remember, for discontinuities, you are looking at the bottom and the bottom only. Okay? So my discontinuities are going to be at x equals -1 and x equals -3. But our x plus 3's do cancel. So what type of discontinuity do I have at -3? Whole, which remember is a removable. And what do I have at -1? Vertical asymptote, which is a non-removable there. Okay. What about -2? It's not a discontinuity. It's actually going to be our x-intercept. No, y-intercept. Which one is it? It's your x-intercept. It's going to be your x-intercept. But the top does not give you discontinuities. The only reason we even care about factoring the top is to see if it'll cancel with the bottom. So we don't pull anything from this right here. That's not a discontinuity. It's okay to have 0 in the top of a fraction, just not in the bottom. Okay, everybody good here? Remember this a little bit, hopefully. All right, now let's talk about some types of problems that we haven't seen. We maybe did 4, but we did not do 3. Okay, so for 3, yesterday on that assignment that you guys had, the bottom 3 problems had one that was kind of like this. I think it was absolute value of x over x or something like that. So it's kind of like this, and we'll find that these problems are all pretty much going to be, they're going to be very similar. So those almost cancel, right? Just about cancel. But the top has absolute value bars and the bottom does not, so we can't just mark them out and cancel them. I am definitely, without a doubt, going to have a discontinuity at x equals -1. And I know that because my denominator here, if I plug in -1, I'd get 0 in the denominator. But I need to know what type of discontinuity that's going to be, and it's a little confusing with this here. So a lot of times when these are given to you, they kind of expect you to recognize what's happening here, and they're not going to give you a calculator. We'll graph it in Desmos in a minute just to see it, but Let's think about making a table for this. So if I do X and Y here, if I plug in, let's say like -3, I would have absolute value of -3 plus 1 over -3 plus 1. And that would give me absolute value of -2, which is +2, over -2. What am I going to get? -1. All right. If I plug in -2, I would have absolute value of -2 plus 1 over -2 plus 1. In the top, I'll get a +1. In the bottom, I'll get a -1. That also gives me -1. All right. If I tried something like -1.5, I can't plug in -1 because it'll give me 0 over 0. If I did that, I would have, on the top, I'd get +0.5. In the bottom, I'd get -0.5. Again, -1. What number am I going to get for pretty much anything I plug in that's below 1? A -1. Get -1, right? All the way up until -1, in which it's undefined, right? What's going to happen if I plug in numbers bigger, right? So let's say I plug in a +1. No, not +1.5. Let's do something like plug in 1. Let's start with 1. So if I plug in 1, right, I would have the absolute value of 1 plus 1 over 1 plus 1. I get 2 over 2. So I would get a +1. What about if I plug in 0? What would I get then? 1 over 1, still +1, right? If I plug in -0.5, I would still get 1, right? So everything above -1, it appears that I'm getting a +1 there. And everything below -1, it appears I'm getting a -1. So what type of discontinuity do you guys think we're going to have here? What does that mean? It's going to be a jump. Because we're not just having like that one hole. We have this line down here at -1 and this one up here at +1. Let's look at it in Desmos just to see it, even though we wouldn't be able to do that. It's helpful to picture it. So y equals absolute value of x plus 1 over x plus 1. And here's what you got. You got just a line, and you jump up to the other line. These would be open circles at the end because it's undefined right there at the end. So this is the case. Now, watch. This is going to be the case for pretty much all problems that look like this. If you have something that would cancel, but you got absolute value bars, it's going to happen for pretty much all of these functions. So if we think about the one that we were looking at yesterday, where I told you just not to do it yet, if I had absolute value of x over x, same thing happens, right? It's just the discontinuity is going to be at 0 instead of at -1. If I did +5 and +5, still have a jump, and it's at -5, right? Because that's where I'd have a 0 in the denominator. If I do something like, I could put the absolute value on the bottom. Y equals, let's do x minus 7 over absolute value of x minus 7. Okay? Now, here, still same thing, 7, I've got a jump. So these types of problems are usually going to produce jumps. I haven't seen them give you anything like crazier where maybe you had absolute value and x squared or something. That would do something different, but I haven't seen those. So this right here would be a jump in the graph. Jumps, are they removable or non-removable? Non-removable. Okay. Questions on that one? You'll see some of those show up. Sometimes they put those on the exam, and they'll be on non-calculator where you can't graph it. So you kind of have to recognize what's happening there, which is really easy to forget about those because it's not something we're going to see a ton of, but they do put them on there sometimes. All right, let's look at 4. This is a composition of functions. We got to take G and plug it into F. So whenever you do these problems, and we did some of these in pre-cal, you got to consider the inside first. Because if the inside is undefined, then f of g of x can't be defined there either. However, our g of x is just x squared plus 3. Do you have any discontinuities on x squared plus 3? Just a quadratic, right? It doesn't have any holes, it doesn't have any asymptotes, it doesn't have any jumps. So it's just a quadratic. So this does not have any discontinuity. So we're going to go right along then to looking at f of g of x, which is going to be 1 over x squared plus 3 plus 2, which if we want to simplify a little bit is 1 over x squared plus 5. Now, whenever we're looking at this, there is maybe a possibility for some discontinuities because we have a denominator in this one, and we know that denominator cannot equal 0. So we want to think about what would make that denominator 0. So if I think x squared plus 5 equals 0, it won't factor. I could solve this, though, or try anyway. X squared is going to equal negative 5. You get rid of that. Oh, what's the matter with that? Yeah, negative under the square root. That's an imaginary number, right? So while we can solve it, we don't get a real number for that. And when you're talking about graphs, graphs are only showing your real numbers, right? If we have an imaginary number, we're going to end up with a hole. Or we're going to it's not going to show on the graph. So that's not really giving us anything because we got that negative under the square root. Is it possible for the denominator to be 0? Think about all the numbers you could plug in there.
Oh, yeah, the negatives give you a positive after the square.
Right. When we square something, we will get a positive, no matter what. Even if we plug in negative 3, right? We will get a positive number right here because when you square something, it's going to become positive. And if you add 5 to it, it makes it more positive, right? Bigger positive than it was before. So this can never equal 0 because you've got a positive plus another positive, which is never going to give you 0. The only way you could make that be 0 is to plug in an imaginary number, which is not what they're looking for on these problems. So this one has no discontinuities. So sometimes it has a denominator that looks like you would have a discontinuity, but when you go to try to solve that, you find that it actually can't ever equal 0. So in this case, this would be defined for all real numbers. You don't have any discontinuities in this one. Okay, questions there? Okay, let's look at piecewise. Okay, so we're going to actually graph this one. I won't make you graph too many, but we're going to graph this one. So we have got to tell whether we have removable or non-removable discontinuities here. So we got to graph this first graph for x is less than or equal to negative 5. So that falls, I'm going to put myself a dotted line right here. We were doing piecewise in Math 3 the other day. And I had them like graph, I still have it up here. Like I made them graph them on sticky notes. I think we did this in pre-cal too. And then I like make them actually cut it apart and throw away the parts you don't need, right? So that's how we do for our piecewise functions. So we're going to graph this, but we're only going to keep the part that's over here less than negative 5. What does x over 2 look like? It's 1/2 x. Very good. This is the same as 1/2 times x, because there is a 1 right there with that x, and if I multiplied that back together, that's x over 1, and it'd give me x in the top, 2 in the bottom, right? So 1/2 x, it has a y-intercept at 0 and a slope of 1/2. So I'm putting the dots over here, but I'm not going to draw the line because I'm not going to use that part of the graph, right? So the line would look like this. but I would only use this piece of it. And I would throw away this part. I wouldn't actually use that over there. And I used an open circle. Why did I use that open circle? It's not equal to right here. Alright, then I have absolute value of x minus 1. What do absolute value graphs look like? These, right? So, which direction has this one moved? To the right 1. So, it's a V, and it has moved to the right 1. So, that would be here, and it's going to look like this. Where am I stopping? 3. So let's put us a dotted line there at 3. The dotted lines are not part of the graph. I'm just putting them in there so I can think about cutting my pieces apart there. So we would have this graph here. Over here on the left-hand side at x equals -5, what type of circle do I need? An open circle or a closed? Closed, because that -5 has the or equal to with it. What do I need over here with the 3? That one's going to be open because I don't have an or equal to there. Okay, square root functions. You should be familiar with the fact that square root functions look like this. But you might not be great at knowing like exact points because, especially in years past, I've not been as worried about graphing by hand. So I know I don't need to start this until I get to 3. You could just plug in numbers, right? If I plug in 3, what do I get? I'll get square root of 4, which is 2, right? So that's right here, okay? Then if I plug in 4, I get square root of 5. I don't know how to graph that. Then I get square root of 6, square root of 7, square root of 8, square root of 9. I do know how to graph that. That would be 3. Right, and so I'm getting this graph that looks like this. What type of circle should I use here at that point? It's an open circle also, because I don't have an or equal to here. Okay, so when I'm looking at this graph, I've got 2 discontinuities, right? At x equals -5, what type of discontinuity do I have? A jump. But at x equals 3, what type of discontinuity do I have? I've got a hole. Okay. The only reason I have a hole is because both of those were open circles. What if I had an or equal to right there with that 3? That'd be a closed circle inside of an open circle, and then we wouldn't have that hole anymore if that were the case. But there were, both of them were open circles, so that was the case. It moves it to the left 1. So what an absolute square root looks like is it would have like a point here, it'd have a point here, and then the next point would be right here. But because we're not using this part of the graph, it starts at that point right there. Okay, there is a way to do this without having to graph it, because sometimes they might be hard to graph or you wouldn't look at it. So I care about right here, I care about this happening. Actually, let me see. Yeah, I care about this happening at -5 and at 3, because these are going to be defined pretty much everywhere for the sections that you're looking at. So I care about these places where they meet. So if I do the limit as x approaches -5 from the left of f of x, from the left, I'm using that top equation. And to find that limit, it's just a direct substitution. I just plug in negative 5 over 2, right? So that's my limit from the left. If I do the limit as x approaches negative 5 from the right of f of x, negative 5 from the right, because we're looking at these two functions, right? That's the absolute value of x minus 1. So if I do that, absolute value of negative 5 minus 1, that gives us absolute value of negative 6, which is 6. Those two do not match, right? And so since those two don't match, I know that I'm going to have a jump in the graph. At 3, I can do the same thing. I would do the limit as x approaches 3 from the left of f of x, and from the left at 3, I would be using absolute value of x minus 1, which would give us 3 minus 1, which gives us 2, and the limit as x approaches 3 from the right of f of x. If I plug in 3 here, that's going to be the square root of 3 minus 1, which is, oh, I'm sorry, that's plus 1, which is square root of 4, which also equals 2. Now, that makes it look like you don't have a discontinuity there. That's why you got to pay attention to your signs right here to see that, oh, they're both open circles, right? So I do have a hole. They match, the limit exists there, but I don't have, I do have to still have a hole. If one of these is or equal to, then it would be continuous at that point, which we'll talk more about tomorrow. Let's see. All right, I'm going to do this. I think I'm not going to do the last example because your book does this a little bit where instead of giving you the problems with like a nice x is less than 1, x is between negative 1 and 1, it gives you these absolute values. So in Math 3, you solve absolute value inequalities, or at least you were supposed to. So maybe that happened. I'm doing it right now in Math 3. So absolute value inequalities, when you have a less than, that is an and problem. So this really means x is less than 1 and x is greater than negative 1. Which if you have numbers, think about that. If you have numbers that are less than 1, but also greater than negative 1, we're talking about negative 1 less than x less than 1, right? That's what this really means right here. You can also think about that distance from 0 is less than 1. So that would be if all the numbers where your distance from 0 is less than 1, that's from negative 1 up to positive 1. Okay. This means our distance from 0 is greater than or equal to 1. Okay? So these are OR problems. So it would be x is greater than or equal to 1, or x is less than or equal to negative 1. So we would be talking, this piece right here, that's talking about these sides of the graph. So when I do these, I at least like to think about these as being rewritten, because I don't like this absolute value stuff that they give us. So I usually either rewrite it or think about rewriting it. So the lowest numbers are these x is less than or equal to negative 1. And the equation we use for that is x. Then in the middle, you would have negative 1 less than x less than 1. And that would be cosine of pi x over 2. And then the last part would be your x is greater than or equal to 1, and that's also an x. So now it looks more like the ones that we saw. So the places we care about are at negative 1. We need to see if these match up. And then we also care about at positive 1, we'll be looking at the middle and the last. So if it's free response, you want to use limit notation. Limit as x approaches -1 from the left of f of x. Well, from the left, that's the top equation. You just plug in -1. That's your answer. And your limit as x approaches -1 from the right of f of x, that's the middle equation. So you're going to have cosine of pi times -1 over 2. So we're doing cosine of -pi over 2, and on our unit circle, -pi over 2 is right here, and the coordinates of that point are 0, -1. Cosine is our x coordinates, so that would be 0. So at x equals -1, do we have a discontinuity? Do these two match? They do not. So we would have a discontinuity. It would be a jump. There. So we would check -1. We also need to check +1. So our limit as x approaches +1 from the left of f of x would be cosine of pi times 1 over 2, which is cosine of pi over 2. That's here, 0, 1. What does that equal? 0. And then if I do the limit as x approaches 1 from the right of f of x, that would be the bottom function. So I'm just plugging in for x, and I would get 1. These two don't match either, so at x equals 1, I would have another jump in the graph. Okay, so I'm not going to do the last example there because I haven't done it. I need to just take it off. I don't like doing those. I don't think you're going to see those on the exam. It's more complicated than it needs to be. So your assignment, I have it on here, it's on Canvas. It's from the textbook, and it will be, let's go there and look. Let me make sure I don't need to make adjustments on this. We're on page 96, 37 through 55 odd, and let me see if there's some of them I need to take off because of that last example. 37 through 55 odd. That assignment is fine. We have looked at a little bit of all of those. What if I had just like a quadratic? What if I had just like f of x equals x squared plus 3x plus 2? What kind of discontinuities does that have? Nothing. It's just a quadratic. It doesn't have any holes or asymptotes. That's just none, right? What about if I've got f of x equals 2x plus cosine x? Nothing. You don't have zeros in the denominator. Cosine's continuous everywhere. Nothing. So you're going to run into some of those, and I usually get questions about those. There are some of these that just don't have discontinuities. You're looking for zeros in the denominator, piecewise functions that don't match up. Those are the sort of things you're going to see. Okay? All right. So time is up. Go ahead and pack up there. All right.
Limit notations are under.
Wonder.